Hello everyone, my name is Prashant and you are here for the GATE Academy's Power Pack sessions on the subject of control systems. These sessions are especially designed for you in order to extensively cover almost all the important topics of the subject. Chances are high that you might get a question from part of these questions, or else part of these questions are going to be indirectly useful for your GATE 2019 exams. So let's look into the questions one by one. The first question is like this, you can see here. Determine the output C for the below system using reduction technique and signal flow graph. So if you look into the block diagram, the system is given to be like this. Here you can clearly see that this is a multiple input system, isn't it? There is one input is this R, another input is this V1, another input is V2, right? So how would you calculate the output for a multiple input system? In the transfer function approach, you have to calculate by using the superposition principle, just like you do in networks or any other subject. So if you have multiple inputs, you first have to calculate the output because of input R nullifying this input V1 and V2. Then you have to calculate the output C because of V1 by nullifying R and V2. Then you have to calculate the output of the system when V2 is present and R and V1 are absent. So let us take the case when R is present and V1 and V2 are absent. So let us make V1 to be equal to 0, that is equal to V2, and only R is present. So this will turn like this. You see, if I nullify V1 and V2, the resultant system is this. If there is no other input except the output from this G1, I can simply take away this particular summing point. I can neglect this summing point and I can straight away join G1 with G2, right? In a similar manner, I can take away this another summing point which joins H2 with H1. Therefore, the system's resultant will be something like this. G1, G2 in cascade and H1 as well as H2 in cascade. If you look here, this is a simple positive feedback loop. So how can you reduce it? By using G1 G2 upon 1 minus G1 G2 H1 H2, just as you do for a simple positive feedback loop, that is G upon 1 plus 1 minus GH. Therefore, R is the input to the system and C is the output of the system. Therefore, C, when only R is present, can be written like this. That implies C, when V1 is equal to V2 is equal to 0, will be is equal to G1 G2 by 1 minus G1 G2 H1 H2 multiplied by R. Therefore, this is the output when only input R is present. So let's look at the output when the other inputs are present. The second case we are going to see is when only V1 is present and R is absent. Let's look into that. So I'm erasing this part. Now, in this case, V1 will be is equal to 0 as well as R will be is equal to 0. Therefore, this will turn something like this. I've just removed V as well as R. That is the reason why I've removed this summing point. Yeah, you can say you can be removing this particular summing point also. There is no problem at all. So here it is H1 and this summing point cannot be removed because V2 is our input of interest. Therefore, V2 will be here. So you can clearly see that the forward path is formed by H1, G1 and G2 and the feedback path is formed by H2. So this can be reduced like this. G1, G2, H1. Because all the three are cascaded and this has to be placed in the forward path. V1 is your input. And in the feedback path, we have H2. Therefore, this is again a simple positive feedback loop. So this can be reduced like this. G1, G2, H1 divided by 1 minus G1, G2, H1, H2. This time V1 is the input and C is the output. Therefore, C, the output C only when V1 is present will be like this. C when V2 is equal to R2 is equal to 0 is equal to G1, G2, H1 divided by 1 minus G1, G2, H1, H2 multiplied by V1 because V1 was the input and this is the particular transfer function when V1 is the only input. So C will be is equal to G1, G2, H1 by 1 minus G1, G2, H1, H2 times V1. This is the output when only in V1 is the only input. right? So now let's nullify V2 as well as R, and let's place this input. V1 is a non-zero input, whereas V2 and R both are zero inputs. Then look into the then we'll look into the output how it is. So V2 is equal to R is equal to 0. So in this case, the system is going to be somewhat like this. In the previous case, we have nullified V1, then this summing point, and we have nullified R, then this summing point. Both the summing points vanished. Whereas in this case, this summing point as well as this summing point is going to be vanished. So the system would turn something like this. G1 here, this summing point have to be present because V1 we are feeding to this summing point only, and this is G2 and this is the output C. Sorry, this summing point can be removed and H2. This is the scenario now. So you can clearly see here from V1 to the output, the input and output are connected by only this particular forward path from V1 to C. Therefore, G2 will be placed in the forward path, whereas this H1, H2 as well as G1, all the three will be placed in the feedback path. Therefore, the resultant will be like this. G2, G1, H1, H2. And V1 is the input and C is the output. Therefore, this is again a simple positive feedback loop. Therefore, it will be is equal to G2 upon 1 minus G1, G2, H1, H2. V1 is the input this time. Therefore, the output when only V1 is present is C. When V2 is equal to R is equal to 0 will be is equal to G2 by 1 minus G1, G2, H2 multiplied by V1. So, this is the output when only V1 is present. When only V1 is present, the output is G2 upon 1 minus G1, G2, H2 multiplied G1, G2, H1, H2. So, it is G1, G2, H1, H2 multiplied by V1. Therefore, when all the three inputs are acting together, the output will be output because of this input, that is V1, output because of this plus output because of this input plus output because of this input. Therefore, you can clearly see here the output because of the first input, that is R, we got the output as G1 G2 by 1 minus G1 G2 H1 H2 multiplied by R, plus when only V1 is present, it is G2 by 1 minus G1 G2 H1 H2 multiplied by V1. When only V2 is present, the output was G1 G2 H1 divided by 1 minus G1 G2 H1 H2 multiplied by V2. Therefore, the overall output of the system is going to be C is equal to output because of R plus output because of V1 plus output because of V2. This is how we calculate the entire output when there are multiple inputs in the system. Just by using superposition, we'll calculate the entire output. So this is how we calculated using reduction techniques. Now we have to calculate using signal flow graph also. So let us obtain the signal flow graph for the given system. So I'm just replacing these blocks, each and every block with signal flow graph branch, and each and every summing point and takeoff point with a node. Just represent this particular summing point with a node, this particular summing point with a node, as well as this particular takeoff point with a node, like this. Now I have to join each and every node, that is G1 will be the gain for this, G2 will be the gain for this, this is H1, and from here we are getting H2. So this is the output C, whereas this is the input R, and these are unity gain branches. So this is the signal flow graph for this particular system, and we have to add these inputs also, that is V1 as well as V2. V1 is here and V2 is here. Right. Now let us reduce the system when only one particular input, that is R, is present, and again only one particular input, that is V1 is present, again V2 is present, like that. So I'm just erasing this. In this particular signal flow graph, let us say only V1 is present and V2 and R1, sorry, only R is present and V1 and V2 are absent. So what I can do is I can just neglect these inputs, that is V2 can be neglected and V1 can also be neglected. Therefore, this is the system when V1 is equal to V2 is equal to 0, whereas R is the only non-zero input. This is the system. So how many forward paths are there in this particular system? There is only one forward path, that is this G1 G2 path. Right? How many feedback paths? One feedback path, H1 H2 path. Right? Therefore, how many loops will be there? Only one loop, G1 G2 H1 H2. Right? Therefore, forward paths, first forward path, that is P1 is equal to G1 G2, and the loop, only loop we have is G1 G2 H1 H2. So only these are the things we require in order to put them in the Mason's gain formula. You already know the Mason's gain formula. Mason's gain formula gives the overall transfer function M as summation of Pk delta k, it is 1 by delta summation of pk delta k, where k runs from 1 to n, where n is the number of forward paths. Pk corresponds to that particular forward path. If it is the first forward path, it is P1. It is second forward path, it is P2. You already know this. And delta you calculate by 1 minus summation of all the loop gains of individual loops plus summation of product of two non-touching loops taken one at a time, right? So in this way you have to calculate, but whereas in this case we don't have non-touching loops and all, we just have only one loop, that is L1, G1, G2, H1, H2. Therefore, just put these two things in this particular formula. So delta 1, there are no non-touching loops for this first forward path, therefore delta 1 will be is equal to 1 minus 0, that is simply 1. Delta 1 is delta calculated by neglecting all the forward paths, all the loops touching to the first forward path. If you are calculating delta 2, you have to neglect all the loops touching to second forward path, and just calculate the same way as you calculate delta. Therefore, put it in this formula, the overall transfer function, that is C upon R, when V1 is equal to 0, V1 is equal to V2 is equal to 0 is equal to P1 delta 1 by delta. Let us calculate delta here. Delta is equal to 1 minus summation of all individual loop gains, that is G1, G2, H1, H2. Therefore, P1 delta 1 by delta, that is equal to G1, G2 multiplied by 1. Delta 1 is 1, and by delta it is 1 minus G1, G2, H1, H2. This is the overall transfer function C by R when V1 is equal to V2 is equal to 0. Therefore, if you want to calculate the output when only input R is present, output C will be is equal to R multiplied by the transfer function G1, G2 upon 1 minus G1, G2, H1, H2. We have seen it earlier also, right? Let us now discuss the case when V1 is the only input present and R and V2 are absent. Then the case will be something like this. V1 is the only input present and V2 is 0 as well as R is 0. Therefore, let us see it here. R is absent, which means I can simply wipe off the input R. Therefore, what is the forward path now? From V1 to C, there is only one path, that is G2. G2 is the only forward path. Therefore, P1 will be is equal to G2. So, how many loops are there? There is only one loop yet. So, let us say the loop starts at this particular node, that is G passes through G2, passes through H2, passes through H1 and passes through G1 and ends at this particular node. Therefore, only one loop, that is G2 multiplied by H2 multiplied by H1 multiplied by G1. It is same as the previous case. That is loop L1 is equal to G1, G2, H1, H2. And let us calculate delta 1. Delta 1 is simply 1 minus 0, that is equal to 1, because there are no forward paths, there are no loops which are not touching the first forward path. Therefore, simply let us put it in the Mason's gain formula, overall transfer function, that is C by, in this case it is C by V1 when R is equal to 0 as well as V is equal to V2 is equal to 0. R is equal to V2 is equal to 0. That implies the output will be G2 upon 1 minus G1 G2 H1, H2. This is the transfer function. Now the output will be C when R is equal to V2 is equal to 0 is equal to G2 by 1 minus G1, G2, H1, H2 multiplied by V1, because V1 is the only input present in this case. Therefore, the output in this case is G2 by 1 minus G1, G2, H1, H2. So, if you want to calculate the output when only V2 is the only input, whereas V1 and R vanished. So, what we have to do, we have to just neglect these two inputs. That is, make these inputs to 0. That is, V and R are made 0 and V1 and R are made 0. Only V2 is the only input present. Right? So for V2, what is the forward path? The forward path in the case of V2 is H1, G1, G2, and only feedback path present in this case is H2. So you can manipulate the forward path gain. So I'm erasing it entirely. Therefore, the forward path gain is P1 is equal to H1 multiplied by G1 multiplied by G2, because that is the only forward path from V2 to C. That is G1, G2, H1. You can write it like this. Delta 1 will be is equal to how much? It is simply 1, because there are no forward paths, there are no loops which are not touching the first forward path. Right. Next, the only loop present is the same. It is H1 multiplied by G1 multiplied by G2 multiplied by H2. Therefore, the loop is G1, G2, H1, H2. Therefore, the overall transfer function is going to be C by V2 when V1 is equal to R is equal to 0 is equal to G1, G2, H1 divided by 1 minus G1, G2, H1, H2. That implies C when V1 is equal to R is equal to 0, G1, G2, H1 divided by 1 minus G1, G2, H1, H2 multiplied by V2, just because V2 is the only input. Therefore, the input when the output C when V2 is the only input will be G1, G2, H1 by 1 minus G1, G2, H1, H2. So, how will you calculate the overall output? The overall output you can calculate by adding each and the components of output because of each and every input. Right? It is the same as the previous case we have seen. That is, C will be is equal to when only R1 is present. When only R is present, the output was G1, G2 divided by 1 minus G1, G2, H1, H2 multiplied by R plus the output when only V1 is present, that is G2 divided by 1 minus G1, G2, H1, H2 multiplied by, because V1 is the only input, the transfer function will be multiplied by V1 plus the output when V2 is present is appearing here itself, that is G1, G2, H1 divided by 1 minus G1, G2, H1, H2 multiplied by V2. Therefore, the overall output is the one enclosed in this particular box. Therefore, we have seen the reduction technique, the output calculated using reduction technique and the output calculated using signal flow graph technique, right? the key area we need to notice here is superposition. When more than one input is present, let us say here there are three inputs which are present. Therefore, what we have done is we have used superposition. We have nullified the other two inputs when one input is present, and we have calculated the respective output, and we have added all the respective outputs to get the entire output, and this is the entire output. So let's go through the second question now. So the question number 2 you can see on the board is like this. For a second order system, the location of poles is known to be -3 plus or minus J7. Calculate the peak time, percentage overshoot, and approximate settling time for plus or minus 2% range. So let's go through the solution, which is like this. The roots are given. Roots are given to be S1 and S2 is equal to -3 plus or minus J7. These are the roots. So what is the standard second order characteristic equation you have? That is standard second order characteristic equation is something like this: S square plus 2 zeta omega n into S plus omega n square. If you solve this particular equation, the roots you will be getting are S is equal to minus zeta omega n plus or minus j times of omega n under root 1 minus zeta square. I have pre-assumed that zeta is between 0 and 1. So if zeta is between 0 and 1, the roots you will get for this particular characteristic equation. It's very easy. If you just equate this particular equation with 0, and how will you calculate the roots? You have that particular formula, that is minus b plus or minus root or b square minus 4ac by 2a. So in that way I've just calculated the roots. The roots I'll get are minus zeta omega n plus or minus j times of omega n under root 1 minus zeta square. Therefore, this will be is equal to, I can write it in short as minus zeta omega n plus or minus j times of omega d. Omega d, where omega d is damped natural frequency and omega n is natural frequency. You already know omega d is omega n under root 1 minus zeta square. Therefore, that is the reason why I've just written omega d like this. Now just compare these with the roots which are given. The roots given are -3 plus or minus J7. So upon comparison, you came to know that zeta omega n is equal to 3 as well as omega d is equal to 7. Therefore, the parameters asked in the question are, the first one is peak time. Peak time, you have the formula for peak time as T suffix P is equal to pi by omega d. Pi by omega d. Omega d is directly available from the roots given for the characteristic equation. That is pi by 7. So if you calculate, you will get some fraction, pi by 7 seconds. So the second parameter asked is percentage overshoot. So what is the formula you have for percentage overshoot? Maximum peak overshoot MP in percentage is equal to e power minus pi zeta by under root 1 minus zeta square multiplied by 100. This is the formula you have for maximum peak overshoot. So from this, can you calculate zeta by under root 1 minus zeta square? So just calculate the ratio of real part to imaginary part. You can have the real part and imaginary part of the roots from the given roots, right, like this, right? Therefore, if you calculate real part to imaginary part ratio, that is zeta omega n divided by omega n under root 1 minus zeta square. Therefore, this omega n and omega n gets cancelled. You are left with zeta by 1 minus zeta square. That is equal to zeta by under root 1 minus zeta square. That is equal to how much? Real part is 3. Of course, minus 3. I'm just taking the magnitude. It is 3 divided by 7. Right? That is what is exactly we require. E power minus pi zeta by under root 1 minus zeta square. This is what is required. So we have calculated this from the given roots. Therefore, maximum peak overshoot, that implies maximum peak overshoot is equal to e power minus pi times of 3 by 7 multiplied by 100. So if you calculate this, you will get some value if you just calculate this, you will get it to be 26%. Please try to use gate calculator only wherever the calculations are necessary, so that you will get habituated to that particular calculator. Right? The online calculator is already available with you as an Android app. Right? Therefore, the percentage of maximum peak overshoot, that is 26%. And the next parameter that was asked to calculate is settling time for 2% band. So settling time for 2% band is given by 4 times of time constant. T suffix s is equal to 4 times of time constant. What is time constant? Time constant is, I'm just writing it here, time constant is 1 by zeta omega n. So from the set of roots given here, you already know what is time constant. Time constant is equal to 1 by zeta omega n, that is 1 by 3. Therefore, 4 times of time constant, it will be 4 times of 1 by 3. It is simply 4 by 3, that is 1.33 seconds. So this is how very simply you can calculate the asked parameters. What are asked? Peak time, maximum peak overshoot, as well as settling time. Right? So now let us proceed to the next question. So the third question which you can see here is something like this. Determine the complete stability information by using Routh criteria for a unity feedback closed loop system modeled by a transfer function g of s is equal to 128 upon s multiplied by s power 7 plus 3 s power 6 plus 10 s power 5 plus 24 s power 4 plus 48 s cube plus 98 s square plus 128 s plus 192. The question is quite long, of course. You'll get familiar with all the conditions that are prevalent in Routh array, right? So the question is like this. G of s is equal to (128) upon s into s power 7 plus 3 s power 6 plus 10 s power 5 plus 24 s power 4 plus 48 s cube plus 96 s square plus 128 s plus 192. This is the open loop transfer function. So, how can you get the closed loop characteristic equation from the open loop transfer function? That is simply the closed loop characteristic equation is equal to 1 plus g of s is equal to 0, because it has already been mentioned that the system is a unity feedback closed loop system. Therefore, the characteristic equation is going to be something like this: s power 8 plus 3 s power 7 plus 10 s power 6 plus 24 s power 5 plus 48 s power 4 plus 96 s cube plus 128 s square plus 192 s plus 128, because in the numerator it is 128. This is 1 plus g of s is equal to 0. This is a closed loop characteristic equation. Therefore, it is quite simple to construct the route array using whatever how big the characteristic equation is, that doesn't matter. It is quite simple to construct the route array. So let's look into the route array construction process. So you can clearly see here, you just write this as s power 8, s power 7, s power 6, s power 5, s power 4, s cube. You have to proceed till s power 0, but there is a reason why I'm just stopping at s cube. So let's look into how we are formulating the route array. So take the coefficients alternatively and place them in row 1. So start with s power 8. The coefficient is 1. Next alternate 10. Next alternate 48. Next alternate 128. And next alternate is again 128. So for the second row, start with 3. 3. Next alternate is 24. Next alternate is 48. Next alternate is 96. And the next alternate is 192. And the next alternate is nothing but, there is nothing, therefore it is 0. Therefore, the next element, how will you calculate the next element? If you already know how to calculate the next element, you just ignore it. But I'm just discussing the procedure how to calculate the next the elements of the next row. So just remember this pattern: multiply 3 with 10. 3 multiplied by 10 minus 1 multiplied by 24. 3 multiplied by 10 minus 1 multiplied by 24 divided by 3. So the next element, you can fill it like this: 3 multiplied by 10 minus 1 multiplied by 24 divided by 3. Right? In a similar manner, you can calculate this coefficient also, that is 3 multiplied by 48 minus 1 multiplied by 96 divided by 3. That is 3 multiplied by 48 minus 96 divided by 3. Again, 3 multiplied by 128 minus 192 divided by 3. 3 multiplied by 128 minus 192 divided by 3. The next can be calculated by 3 multiplied by 128 minus 1 multiplied by 0 divided by 3. That is simply 128. Right? So even these remaining coefficients, you can replace them by calculating their actual values. You can replace these coefficients with their actual values. The actual value you are going to get in this row is, it is 2 here, 16 here, 64 here, and it is 128 already. Right? After 128, you can put a 0 if needed. Right? So in a similar manner, you have to calculate the next rows also. How to calculate the other row? 2 multiplied by 24 minus 3 multiplied by 16 divided by this 2. That is 2 multiplied by 24 minus 3 multiplied by 16 divided by 2. 2 multiplied by 96 minus 3 multiplied by 64 divided by 2. 2 multiplied by 96 minus 3 multiplied by 64 divided by 2. Again, 2 multiplied by 192 minus 3 multiplied by 128. 2 multiplied by 192 minus 3 multiplied by 128 divided by 2. The next element is 2 multiplied by 0 minus 3 multiplied by 0, that is equal to 0 anyways. Therefore, if you calculate these terms, if you start calculating this 2 multiplied by 24 and 3 multiplied by 16 divided by 2, all these terms, the entire row is going to become 0. So this is going to be equal to 0. 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 And this is anyways 0. So an entire row is 0. If you look here, an entire row is 0. So in this case, what you have to do is you have to construct the auxiliary equation. So how to construct the auxiliary equation? The auxiliary equation will be constructed from the previous row. So what is the previous row here? This s power 6th row. Therefore, the auxiliary equation is going to be something like this. You can write the auxiliary equation to be 2s power 6 plus 16s power 4, 16s power 4, because from s power 6 these are the coefficients of the alternate s terms. Therefore 2s power 6, the next is 16s power 4, and the next is 64s square, and the next is 128 is equal to 0. This is the auxiliary equation, and you already know the auxiliary equation is also the factor of, the auxiliary equation is going to be the factor of your characteristic equation. Therefore, the roots of auxiliary equation will be the roots of the system also. Right? It is 2s power 6 plus 16s power 4 plus 64s square plus 128 is equal to 0. In order to proceed for constructing this Routh array, you just have to differentiate this auxiliary equation with respect to s. You just differentiate the auxiliary equation with respect to s for once and equate and the coefficients you get, the corresponding coefficients you get, you have to replace this particular row with those coefficients. Therefore, the differentiation will be something like this: 2 into 6, that is 12s power 5 plus 16 into 4, that is 64s power 3, 64s power 3, and 64 into 2, that is 128s. So replace the next row with these coefficients, that is 12, 64 as well as 128. I'm just replacing these coefficients with this now. So it is 12, 64 and 128. So just by replacing these coefficients, the zero coefficients with these, we have to proceed constructing the auxiliary equation. Therefore, if you go with the same process, the process is 12 into 16 minus 2 into 64 divided by 12. 12 into 64 minus 2 into 128 divided by 12. So if you start constructing the auxiliary equation, if you proceed further, you will get these values. I'm just giving the values here directly. That is 5.33, 42.67, 128. This is anyway 0, therefore this is also 0. The next row you will be going to get minus 32.06, and the next is minus 160.18, and the next is 0. This is anyways 0. So I'll be just continuing this particular route array at the top of the board. I'm just erasing this one. So s square, s power 1 and s power 0. So if we proceed further, in the s square row you will be going to get 16.04. The next element is 128. The next element is 0 and thereafter zeros. And the next element here in this row is 95.66. The next element is 0 and zeros thereafter. And here it is 125. This is 128. This is clearly evident. This into this minus this into 0 upon this. That is 128. So this is the route array for the given system. So let's check for number of sign changes in the first column. Therefore, this is the first column. In this particular first column, check for the number of sign changes. So it was a positive here, positive number here, positive number 2, negative number. This is one sign change, right? This is a negative number here. From a negative number to a positive number. Therefore, from a negative number to a positive number, it is another sign change. Therefore, how many number of sign changes in total? 1 and 1. Therefore, there are 2 sign changes in total. There are 2 sign changes in total. For 2 sign changes, there must be 2 roots lying in the right half of S-plane. 2 roots must be lying in the right half of S-plane, and please note this point: the degree of auxiliary equation is 6, right? All the roots of auxiliary equation will be going to be symmetrical. I mean, every pair of roots that are produced by this auxiliary equation are going to be symmetrical, always symmetrical about origin, right? So for this, we can say a pair of roots in the right half, a pair of roots in the left half. All the 4 are symmetrical. What about the remaining 2? Those 2 will also be symmetrical about the origin, but they will not be on the right half of S-plane, because only 2 can lie on the right half of S-plane just because of 2 sign changes. Then where are the other 2 roots going to be? They must be lying on the j omega axis. Therefore, after erasing this, we'll see how the pole plot will be. Therefore, let us say this is the S-plane. Let us say we are representing the S-plane with the real and imaginary axis like this. So this is the imaginary axis. Let us say the j omega axis, and this is the real axis, the sigma axis. So after the auxiliary equation we had two sign changes, which means two poles must be on the right half of S-plane. But how are they going to be? They must be the two pairs of poles must be symmetrical about origin, which means two poles here, and the symmetric pair is going to be on the left half like this. The symmetric pair, the corresponding symmetric pair is on the left half. The degree of auxiliary equation is 6. We have already noted it. Therefore, for a sixth degree equation, you must be having 6 roots. I've already said auxiliary equation is nothing but the factor of the characteristic equation. It is a factor of characteristic equation, means the roots of auxiliary equation are going to be the roots of characteristic equation as well. Therefore, the other pair of roots are going to be symmetrical about the origin in some manner like this. The overall characteristic equation is 8th degree equation. If it is an 8th degree equation, that must be having 8 roots. 6 roots we have shown here. The other set of 2 roots might be a pair of real roots, or else a pair of complex conjugate roots lying in the left half of S-plane. Right? They can be a pair of real roots, they can be a pair of complex conjugate roots also. They can be anything lying in the right half of S-plane. Therefore, we have to give the complete stability information. How can we give the complete stability information? The system is unstable with 2 poles lying in the right half of S-plane and 2 poles on the j omega axis and 4 poles on the left half of S-plane. Therefore, the system is unstable with 2 right half S-plane poles and 2 poles on imaginary axis. 2 poles on the imaginary axis and 4 poles on the left half of S-plane. 4 poles on the left half of S-plane. Questions might be asked like this. You might be asked that the number of poles strictly lying on the left half of S-plane. Lying strictly in the left half of S-plane means the poles lying on the j omega axis should not be counted. Therefore, the number of poles strictly lying in the left half of S-plane will be how many? They will be 4. And you might be asked a question, if it is an objective type or else a fill in the blank type, you might be asked a question, the number of poles on the j omega axis or else the number of poles on the right half of S-plane. So whether it is the number of poles on right half of S-plane or number of poles on the j omega axis, it is 2. But please remember, this is the most prominent question. This is asked many times. The number of poles lying in the left half of S-plane, that is strictly lying in the left half of S-plane, are only 4, not 6. The most common mistake people do here is, after getting 2 sign changes, they'll think that there will be 2 poles in the right half of S-plane, and they forget that there are 2 poles on the j omega axis just because the auxiliary equation is of 6th degree. Right? If it is a 6th degree equation, then there will be 2 poles on the j omega axis and 4 poles will be strictly lying to the left half of S-plane. So let's move on to the next question now. So the fourth question you can see here is something like this. Draw the root loci of the system showing all the relevant points for open loop transfer function of the system given by g of s is equal to k upon s multiplied by s square plus 4s plus 8. So it was asked to construct the root locus, and the open loop transfer function of the system is given as g of s is equal to, question number 4, open loop transfer function g of s is equal to k by s multiplied by s square plus 4s plus 8. So this is the open loop transfer function. So for this particular open loop transfer function, if the system is made to be a unity feedback closed loop system, we have to construct the root locus, and we have to find out all the points, that is the breakaway points, the points of intersection with the imaginary axis and all, right? Therefore, so let us consider the S-plane is like this. So one root is already at origin, one pole is at origin. Therefore, this particular pole I can mark here, right? In order to find out the other two poles, the location of other two poles, I just have to factorize this particular equation. Just factorize this using that quadratic, just find out the roots of this particular quadratic equation, that is minus b plus or minus root over b square minus 4ac by 2a. If you solve them, you will get s is equal to minus 2 plus or minus j2. You just have to solve using that particular basic quadratic equations, right? Therefore, let us say this is minus 1 somewhere here and minus 2 plus or minus j2 means one root is somewhere here and the other root is going to be somewhere here. Therefore, we need to plot the root locus for this particular configuration. For the given configuration, we have to plot the root locus. So it is quite evident from the given system, the number of poles is 3, that is number of poles p is equal to 3 and number of zeros z is equal to 0. Therefore, p minus z is equal to 3 simply, right? Therefore, the number of asymptotes are going to be equal to p minus z. The number of asymptotes in the root locus is given by p minus z, that is 3. If p minus z is equal to 3, then the angle of asymptotes, let us say phi suffix a, are going to be 60 degrees, 180 degrees and 300 or minus 60 degrees. So you can calculate the angle of asymptotes from this particular formula. Phi suffix a is equal to 2q plus 1 by p minus z multiplied by 180 degrees. So where q runs from 0, 1, 2, 3, so on. But in this case, p minus z is simply is equal to 3. Therefore, q runs till 0, 1 and 2. Q is, if you put q equals 0, you will get 60. If you put q equals 1, you will get 180. If you put q equals 2, you will get 300. So these are the angles. Now calculate the centroid. Centroid is sigma is equal to, I am just separating this portion, root locus portion with the calculation portion like this. So sigma will be is equal to how much? Summation of all the poles minus summation of zeros divided by p minus z. Therefore, summation of all the poles, that is minus 2 plus j2 minus 2 minus j2. You will get minus 2 minus 2. Minus, there are no zeros, therefore it is 0 divided by 3. Therefore it is minus 4 by 3. It is simply minus 4 divided by 3. So centroid is going to be, centroid is equal to minus 1.33. Therefore, all the asymptotes are going to intersect. Centroid is nothing but the point of intersection of asymptotes. Therefore, all the asymptotes are going to intersect at minus 1.33. Therefore, this particular point is minus 1.33. Therefore, the asymptotes are at angles 60 degrees, minus 60 degrees, and the other angle is 180 degrees. This is the pattern of the asymptotes, right? Therefore, upon increasing the open loop gain K, we need to know how the roots are moving. So in order to know this particular thing, so we have complex set of roots. So in order to know this particular thing, we need to find out angle of departure. So how to find out the angle of departure? We'll see the procedure here. We have both numerical calculation procedure as well as geometric procedure, but the procedure a smart guy adopts is always geometric procedure. Let us say we have a pole here. Where are the other poles? Minus 2 plus 2j and minus 2 minus 2j. The other poles are here like this. Therefore, in order to find out the angle of departure at this particular pole, you have to find out the phase of the system at this particular pole. Phase of the system at that particular pole means summation of angles of elevation because of zeros minus summation of angles of elevation because of poles at this particular pole. You can say when S is equal to minus 2 plus j. You already know this particular root is going to be minus 2 plus j and the other root is going to be minus 2 minus j. So in order to find out the angle of departure, just draw a vector from each and every pole to this particular pole. Let us say this is the particular pole. From this pole, draw a vector like this. And from this pole, draw a vector like this. Right? So calculate the angle of elevation of each and every vector with respect to the positive real axis. So you need to calculate this particular angle as well as this particular angle. So this pole is exactly overhead of this pole. This minus 2 plus j pole, this is minus 2 plus 2j and this is minus 2 minus 2j. This particular pole is exactly overhead of this particular pole. Therefore, the angle of elevation is going to be 90 degrees. It is quite evident from the figure also. It is 90 degrees. What about this? So you see here from origin to minus 2, the distance is 2 units. From this particular point to this particular point, the vertical distance is 2 units. 2 units and 2 units. Therefore, this particular angle, this interior angle is going to be 45 degrees. What about this exterior angle? This exterior angle is this angle plus this angle. It is quite evident that both are on a same straight line, right? Therefore, this exterior angle is going to be 180 minus 45 degrees. That is 135 degrees. Therefore, you have to calculate summation of angles of elevation because of 0. There are no zeros. Therefore, summation of angles of elevation because of 0 will be is equal to 0. And summation of angles of minus summation of angles of elevation because of poles. This angle of elevation is 90 degrees, whereas the other angle of elevation is 135 degrees. So the entire angle, that is summation of the phase of the system at this particular pole is going to be is equal to what? That is equal to minus 225 degrees. But angle of departure, we have a formula that phi d, we actually get this formula from the phase condition. We have angle of departure is equal to 180 plus the phase of the system at this particular pole. Phase of the system at this particular pole is minus 225 degrees. So 180 minus 225, it is going to be minus 45 degrees. Therefore, the angle of departure is going to be minus 45 degrees. So this particular pole is going to depart, that is minus 2 plus 2j. This particular pole is going to depart at minus 45 degrees like this. It is going to depart from its position at minus 45 degrees like this. I am just indicating the angle of departure. The angle of departure should be minus 45 degrees. So you might be getting a doubt. How would this follow this particular pole if it is departing at this angle? It is just departing at this angle. It doesn't mean that it will go in this particular angle only. As gain is increased, it might deviate from its path and go along this asymptote. Therefore, the asymptote you are going to get, this departs at minus 45 degrees and will try to follow its asymptote as the gain is increased. So this is how the root locus for this particular pole is going to be. So now look at the other pole. You already know that root locus is always symmetrical about the real axis. If it is symmetrical about the real axis, the angle of departure for this particular pole is going to be the negative of angle of departure for this particular pole. If it is minus 45, the angle of departure for this particular pole should be plus 45. Therefore, the root locus for this particular pole is going to be like this. So later on, it is going to follow its asymptote in this manner. Right? Therefore, the pole departs, this pole departs at 45 degrees, whereas this pole departs at minus 45 degrees, and later on, they'll follow their corresponding asymptotes. This is how the root locus is going to be. And what about this pole? So it is a pole on the real axis. On the real axis, root locus exists only to the left of odd numbered critical frequency or odd numbered corner frequency. Therefore, this is the only critical frequency on the real axis. That is, its number is 1. So don't confuse its number with its location. So I'm just giving numbers to the persons who are lying on this particular real axis. Therefore, the number of this, he is the first person, therefore the number of this person is 1. Therefore, he is going to move left. This particular pole is going to move to the left on the real axis. Therefore, this is how the root locus of this particular system is going to look like. But we need to calculate, we still need to calculate these points. That is points of intersection with the root locus. You can calculate the breakaway points also, but you are going to get some invalid breakaway points. Therefore, that doesn't give you a valid breakaway points, means there is no breakaway. There is no breakaway between the poles. There is no breakaway in the root locus. Therefore, see here, to calculate the closed loop, to calculate the points of intersection with the j omega axis, you just need to calculate, you just need to obtain the closed loop characteristic equation. Closed loop characteristic equation is equal to 1 plus g of s is equal to 0. So g of s is given to be k upon s into s square plus 4s plus 8. Therefore, 1 plus g of s is going to be s cube plus 4s square plus 8s plus k is equal to 0. This is the closed loop characteristic equation. Just place this equation in route array and obtain the condition for marginal stability. If the roots are intersecting the j omega axis, means they are on the j omega axis. If the roots are on the j omega axis, then the system is marginally stable. Therefore, put this particular characteristic equation in the route array. S cube s square s power 1 s power 0. So it is 1, 8, 4, and the next alternate coefficient is k. Therefore, here we are going to get 4 into 8 minus k divided by 4. That is 8 minus k by 4. And here it is 0 anyways. Here it is this into this minus this into this upon this particular value. So you will get k here. For the system to be marginally stable, an entire row corresponding to odd power of s must be 0. Therefore, let us make this particular row to be 0. If this particular row is 0, this element 8 minus k by 4 is going to be 0. If 8 minus k by 4 is equal to 0, then what is the value of k? K is equal to 4 times of 8, that is equal to 32. So we can call this particular value as marginal gain, that is k marginal. Open loop, this particular open loop gain is going to make the system to be marginally stable. That is the reason why I called this particular value as marginal gain. Therefore, obtain the auxiliary equation by putting this particular value of k in the auxiliary equation row. Therefore, how will you obtain the auxiliary equation? You have to obtain the auxiliary equation from this particular row. So it is, auxiliary equation is going to be 4s square plus k is equal to 0. So what is the value of k? K is 32. Therefore 4s square plus 32 is equal to 0. And if you solve for s, you will get s is equal to plus or minus j2 root 2. If you solve for s, you will be getting s is equal to plus or minus j2 root 2. We have already discussed in the previous question that auxiliary equation is also a factor of the characteristic equation. Therefore, roots of auxiliary equation are going to be roots of characteristic equation as well. Therefore, these roots are going to be the characteristic equation as well. These roots are nothing but the points of intersection of the root locus with respect with the imaginary axis. This root is going to be s is equal to j2 root 2, and this particular root is going to be s is equal to minus j2 root 2. Hence, we have obtained the points of intersection of the root locus with the imaginary axis also. Of course, you can solve for the breakaway points, but you'll get some complex values, which means the breakaway points are invalid. So let's move on to the next question now. So the next question, question number 5 is, as you can see here, is like this: g of s, h of s is equal to k by s into s plus 1 into s plus 4. Sketch the root locus of the system. Determine, under that, the first question is determine the value of k for which the system is at the verge of instability. And the second question is, if the constant damping ratio line zeta is equal to 0.5 intersects the locus at a distance of 1 unit from the origin, find out the value of k at the point of intersection and the gain margin at that particular point. Therefore, the question is like this. Question number 5. G of S is equal to K by S into S plus 1 into S plus 4. Just like the previous question, let us divide the board into two equal halves, so that at one part we can look at the root locus profile, and on the other part we can look at the calculation part. There is a pole at origin, that is this pole, and there is a pole at minus 1. This factor corresponds to the pole minus 1, and there is a pole at minus 4 also. So these are the configurations, these are the placement of open loop poles in the S plane. This plane is nothing but S plane. Therefore, you already know root locus exists on the real axis only to the left of odd numbered critical frequencies. The first critical frequency is this, only to the left of this the root locus is going to exist. Whereas this critical frequency is the second numbered critical frequency, which means to the left of this root locus doesn't exist. And to the left of this particular frequency, this is the third critical frequency, therefore root locus is going to exist to the left of this particular critical frequency also. Therefore, the root locus, I'm just marking the region like this, the root locus is going to exist on the real axis in this region and on the real axis in this region as well. I'm not giving the direction now, I'll be giving the directions whenever necessary. I'm just indicating the region with this particular red. So the next thing is we need to calculate the number of asymptotes. How many number of asymptotes are there in this particular how many number of asymptotes will we get? That is P minus Z. P is equal to 3 and Z is equal to number of poles is 3 and number of zeros is 0. It is clearly evident from the system. Therefore, P minus Z is going to be 3. So we have already seen this case in the previous example. If P minus Z is equal to 3, then angle of asymptotes are going to be 60 degrees, 180 degrees, and 300 degrees, or else you can say it to be minus 60 degrees. So how to calculate this particular centroid? Centroid is the point of intersection of asymptotes. So we can calculate that by summation of poles minus summation of zeros upon P minus Z. Therefore, summation of poles, what are the poles? Poles, one pole at origin, one pole at minus 1 and another pole at minus 4. Therefore, minus 1, minus 4, minus of zeros are nil. Therefore, divided by P minus 1. This is minus 5 divided by 3. Therefore, centroid value is minus 5 divided by 3. If you calculate the exact value of this is going to be somewhere at 2 point something. Sorry, not even 2 point something, it is 1 point something is going to be the position of centroid. So let it be minus 5 by 3 itself. So it is, the centroid is going to be somewhere here. The angle of asymptotes are going to be 60, 60 and 180 degrees. So these are the configurations of 3 asymptotes. Therefore, in between these two poles, there must be a breakaway point. And after this pole, there are no other zeros or poles, therefore there is no breakaway or break-in point. Therefore, in between these two poles, there must be a breakaway point. Let us calculate where the breakaway point is going to be. So, from the closed loop characteristic equation, that is 1 plus G of S 1 plus g of s is equal to 0, you can write the value of k to be k is equal to minus s into s plus 1 into s plus 4. Can we write it like this? Right. Therefore, k is equal to minus s cube plus 5s square plus 4s. K is equal to this particular value. So in order to find out the breakaway points, you need to equate the value of dk by ds to 0. What is dk by ds from this? We can get 3s square plus 10s plus 4 is equal to 0. Therefore, if you solve this particular equation, if you solve this particular equation in terms of s, you will get the breakaway points. The breakaway points calculated by finding out the roots of this particular equation are like this. S is equal to minus 0.4658 and minus 2.8685. So these are the two breakaway points. So in the case of root locus, a point within the root locus, that is between minus 1 and 0, this point exists. Whereas this point minus 2.8685, this exists somewhere here. Let us say this is minus 2.8685, whereas the other point is minus 0.4658. This point exists here, minus 0.46. Therefore, this breakaway point is part of root locus, whereas this breakaway point is not a part of root locus. This might be a part of complementary or inverse root locus, but this is not a part of this particular root locus. Therefore, this is not a valid breakaway point in this case. The only valid breakaway point in this case is this minus 0.46. Therefore, the roots are going to break away from this particular point and the roots will break away and follow their asymptotes. I am taking the breakaway point somewhere here. The roots are going to follow their asymptotes in this manner. Therefore, the directions of the root locus are going to be in this way. Both the roots approach each other and they break away. They break away from the real axis at right angles and they go along their asymptotes. Therefore, I am just erasing it for other convenience. The breakaway point we got here is minus 0.4658. So this is about the first question. The first question is asked to be find out the value of k at which the system goes unstable. That is k for marginal stability. That is, we need to find out the points of intersection of the root locus with respect to the imaginary axis. Therefore, in order to find that particular point, just place the closed loop characteristic equation in Routh array and obtain the value of k marginal as we have done in the previous problem. Therefore, the closed loop characteristic equation is 1 plus g of s is equal to 0. 1 plus g of s is equal to 0. That is equal to s cube plus 5s square plus 4s plus k is equal to 0. It is quite simple to calculate this. Therefore, put this particular equation in the Routh array. Routh array is s cube, s square, s power 1, s power 0. The coefficient we are going to place here is 1. The alternate coefficient is 4, 0 here, 5, k and 0 here. how will we calculate the next coefficient? That is 5 multiplied by 4, 20. You can write it as 4 minus k by 5. This is anyways 0, and here it is k itself. Therefore, for the system to be marginally stable, an entire row corresponding to odd power of s should be 0. So only this row can be 0. So in order to make this row to be 0, we must equate this element with 0. Therefore, 4 minus k by 5 is equal to 0. That implies k is equal to 20 degrees. I'm sorry, k equals 20, not 20 degrees. K equals 20. So if you put this particular value of k in this equation, you can get the auxiliary equation and you can calculate the points of intersection. But that was not asked here. We were just asked to calculate the value of k for marginal stability. Therefore, k for marginal stability, that is k suffix marginal, is equal to how much? It is equal to 20 units. Therefore, k marginal for the given system is 20 units. So let's look into the second question of the system. Second question of the given question. Second sub question. That is, if the constant damping ratio line zeta is equal to 0.5 intersects the locus at a distance of 1 unit from the origin, find out the value of k at the point of intersection and gain margin. So it is said that if the constant damping ratio line, let us take the constant damping ratio line to be here, somewhere here, like this. So this particular line corresponds to constant damping ratio, that is zeta is equal to 0.5. If zeta is 0.5, we need to calculate the value of theta. So zeta is nothing but cos theta. Zeta is equal to cos theta. If this is equal to 0.5, that implies theta is equal to 60 degrees. This particular angle, this theta is equal to how much? This is equal to 60 degrees. So at this point of intersection, let us call this point of intersection as A. At this particular point A, we need to find out the value of k and gain margin if the roots are at this particular point. If at least one root is at this particular point, we need to find out the gain margin. Therefore, so in order to find that particular thing, we need to find out this point A, or else the length of this point from each and every pole, right? So this point, how can we calculate? The length is given. Length is given to be 1 unit. Length from origin to this particular point is 1 unit. Cos theta is 1 by 2. That is adjacent side divided by the hypotenuse is equal to 1 by 2. Which means, what is this adjacent side going to be? I'm just drawing this particular, let us name this as B, and I'm just drawing this particular triangle in the left side of the board like this. So from the triangle you can see that this angle is 60 degrees, this distance is 1, and the triangle is OAB. This is 90 degrees. So cos theta is equal to 0.5. That is adjacent side divided by hypotenuse is 0.5. That implies hypotenuse is 1. Therefore, adjacent side is going to be equal to 0.5. Therefore, if you put adjacent side distance here, that is equal to 0.5. So if cos theta is this, sin theta is going to be root 3 by 2. If cos theta is 1 by 2, sin theta is equal to root 3 by 2. So root 3 by 2 will be the height of this particular triangle. This is root 3 by 2. So this is root 3 by 2. This length is root 3 by 2. Whereas this particular length is 0.5. So if this length is 0.5, from O to B it is 0.5, from B to this pole it is again 0.5, because from O to this pole it is 1 unit, right? This pole is at -1. So 1 unit minus 0.5, it is 0.5. This length is going to be 0.5. So draw a vector from this pole to this particular point and call this particular length as L2. I am calling this particular length as L2, and draw another vector from the other pole also. This is L3 and this is L1, right? So in order to find out K at this particular point, the gain at this particular point, you can get it from the magnitude condition as K is equal to L1 multiplied by L2 multiplied by L3. K is L1 multiplied by L2 multiplied by L3. L1 is anyways 1, and you can calculate L2 from this right angle triangle. This side is 0.5. If this side is 0.5, you can see this particular triangle, this complete triangle has been divided into two equal halves by this. If this is 0.5 and the vertical height is root 3 by 2, this L2 is again going to be 1. L2 is also is equal to 1. That is, I can write it more clearly, that is 1 by 2 whole square plus root 3 by 2 whole square, that is going to be 1. So what about L3? In order to find L3, we need this adjacent side, I mean the base as well as height of this triangle. Height of the triangle is already known, that is root 3 by 2. And the base of the triangle, see, from here to here the distance is 0.5, and from here to here the distance is 4. Therefore the distance from this pole to this particular point B is 4 minus 0.5. Therefore this particular distance, I will write this particular distance as 3.5, or else you can write it as 7 by 2. If this is 7 by 2, can you calculate L3? It is very easy, because we know the base and height of the triangle. You need to calculate the hypotenuse. Therefore L3 is equal to under root 7 by 2 whole square plus root 3 by 2 whole square, that is equal to 49 by 4 plus 3 by 4. You'll get this particular value as root 13. This value will be is equal to root 13. Therefore value of K is root 13 multiplied by L2 is 1, L1 is also 1 multiplied by 1 multiplied by 1. Therefore K is equal to root 13. What is this K? K is the magnitude of open loop gain at point A. Therefore, in order to indicate this, I am indicating this K with K suffix A. It was also asked to calculate the gain margin at when the roots are at this particular point. So, in order to calculate gain margin, you again have a formula. You cannot say it as a formula, you just have to find out the amount of gain that you can still increase before the system goes to be unstable. So gain margin can be calculated from this particular thing, that is 20, this is 20 log modulus of K suffix A, K marginal divided by K suffix A. K marginal divided by K suffix A is clearly 20 divided by root 13. Therefore, K marginal divided by K suffix A is 20 divided by root 13. This is 20 log 20 divided by root 13. Therefore, the value of the gain margin you are going to get, gain margin will be is equal to how much? 14.88 decibels. In decibels, the value of gain margin is going to be 14.88. What is gain margin? Gain margin is nothing but the amount of gain you can still increase before the system goes unstable. Therefore, at what value of gain the system is going unstable? The system is going unstable at 20. Therefore, if you find out the ratio, you will get the gain margin. So, if you find out the value in decibels, you will get gain margin in decibels. That is 14.88 decibels. That's all with this question. And let us move to the next question. So the next question, as you can see here, is like this. Sketch the Bode plot of the feedback system whose open loop frequency function g of j omega is equal to 10 by j omega multiplied by 0.1 j omega plus 1 multiplied by 0.05 j omega plus 1. And the sub question 1 among the two questions is determine the gain margin and phase margin, and the second question is find the open loop gain K for a gain margin of 20 decibels, which means the value of K if the gain margin should be 20 decibels, right? Therefore, the solution can for this particular system is, from the question it is clearly evident that the system is, the question is from the Bode plots, right? This is the question number 6. The frequency function, that is g of j omega, transfer function g of j omega, is given by 10 upon j omega multiplied by 0.1 j omega plus 1 multiplied by 0.05 j omega plus 1. So we can simply write this particular time constant form of the frequency function in pole 0 form also. Therefore, then we'll get poles at s is equal to 0, s is equal to minus 10, as well as s is equal to minus 20. These are the poles for the given particular system. So I'm just again dividing the board into two equal halves, where on the right I'm going to plot the Bode plot, on the left we'll be doing some calculations required. Therefore, this is the magnitude plot. Let us say magnitude in decibels, and this is the frequency on logarithmic scale. Let us start with 1, 10, 20, 30, so on, 20. So after 10, it must be 100 in the log scale, but I'm just zooming this part to show you, right? So what is the gain of the system when omega is equal to 1? Therefore, this is the given transfer function. So from the transfer function is already in the time constant form. So the Bode plot is going to intersect the frequency axis. This particular axis at some point. This point is given by 20 log k by omega at omega is equal to 1, right? When omega is equal to 1, what is the value of 20 log kdc by omega? Kdc, if the type of the system is neglected, the kdc is clearly visible, that is kdc value is 10. Therefore, it is 20 log 10 by omega when omega is equal to 1. This is going to be equal to 20 log 10, that is equal to 20 decibels. Therefore, this axis, the plot is going to intersect this particular axis at 20 dB, right? This particular point is going to be 20 decibels. And from here, the plot is going to decay at a rate of minus 20 dB per decade. Minus 20 dB per decade, just because it has a pole at origin. Therefore, initial slope of the plot is going to be minus 20 dB per decade. So at 10 radian per second, it is going to encounter another pole. Therefore, from here the slope becomes minus 40 dB per decade. From here, the slope has to become minus 40 dB per decade. Within 1 decade, the plot is going to decrease by 40 decibels. Let us say 20 is somewhere here. So the slope has now become 40 dB per decade. After 20, it has encountered one more pole. Therefore, its slope is going to be minus 60 dB per decade. Minus 60 decibels per decade. Here the slope is minus 40 decibels per decade. Therefore, it is asked to calculate gain margin and phase margin. The advantage of plotting this gain plot here itself is you can simply find out the gain, easily find out the gain crossover frequency. That is, the system is crossing the 0 dB line at omega is equal to 10 radian per second. At omega is equal to 10 radian per second, the plot is crossing 0 dB line, which means gain crossover frequency omega suffix gc is equal to 10 radian per second. So it was also asked to calculate, plot the frequency response, the phase response with respect to frequency. Therefore, phase of the system, from this, the phase of the system is clearly evident. Phase of g of j omega is equal to how much? Minus 90 degrees minus tan inverse of omega by 10 minus tan inverse of omega by 20 phase. So we can draw an approximate plot also, but let us refine the phase plot just by taking some values of frequency and calculating the values of corresponding phase. So I am tabulating this in this manner. Here it is frequency in radian per second, omega in radian per second, and on the other hand it is phase, that is phase of g of j omega in degrees. So let us tabulate the data as follows. So when omega is exactly is equal to 1 radian per second, the phase, if you calculate, if you put omega is equal to 1 in this, you are going to get minus 98.57 degrees. If it is 10, the phase is minus 161.56 degrees if you calculate. If it is 20, it is minus 198.43 degrees. So if it is 30 radian per second, the phase is minus 217.87 degrees. If the phase is 40, then if the frequency is 40 radian per second, then the phase is going to be minus 229.4 degrees. Minus 229.40. So let us plot the phase plot on the same frequency scale. Here it is 1, here it is 10, 20, 30, 40, so on. Therefore, the phase initially starts at minus 90 degrees. Before omega is equal to 1, it is going to start at minus 90 degrees. But exactly at omega is equal to 1, it is going to be minus 98.57. Therefore, I am just showing minus 98.57 somewhere here. When omega is equal to 10 degrees, it is minus 161.56. At omega is equal to 10 degrees, it is minus 161.5. At omega is equal to 20, it is minus 198.43. At omega is equal to 30, it is minus 217.87. At omega is equal to 40, it is minus 229.40. Therefore, if you join all these, you are going to get the phase response of the given system, phase plot of the given system. Of course, for gate, plotting the phase response is not needed. You just have to find out the phase crossover frequency. Let us see directly from this, how can we find out the phase crossover frequency? Phase crossover frequency, in order to find out phase crossover frequency, you have to equate the phase of the system with minus 180 degrees, right? So, phase of the system, phase plot of the system intersects the minus 180 degrees line at phase crossover frequency. Therefore, before this, it is just minus 161.56, and here it is minus 198.43, and here it is minus 217.87, so on. But it is crossing the 180 degrees line at some particular frequency, and this particular frequency we need to find out in order to find out the gain margin of the system. So phase crossover frequency, in order to find out the phase crossover frequency, equate the phase of the system, that is minus 90 minus tan inverse of omega by 10 minus tan inverse of omega by 20 with minus 180 degrees. Therefore, equate the phase of the system with minus 180 degrees. So upon solving this, you will get tan inverse of omega by 10 plus tan inverse of omega by 20 is equal to 90 degrees. Apply tan on both sides. That implies omega by 10 plus omega by 20 by 1 minus omega square by 200 is equal to infinity. That implies 1 minus omega square by 200 is equal to 0. If this is infinity, which means denominator is 0. That implies if you solve for it, if you solve for omega, you will get omega is equal to root 200 that is equal to 10 root 2 radian per second. This particular value of omega is nothing but the phase crossover frequency omega PC, omega suffix PC. Therefore, this is phase crossover frequency omega suffix PC. So we have phase crossover and phase at phase crossover, gain crossover and gain and phase, as well as phase at phase gain crossover. Gain crossover is at 10 radian per second and phase at gain crossover is minus 161.56. We have already calculated this. Therefore, phase margin is equal to phase of G of j omega at gain crossover frequency, that is omega GC, plus 180 degrees. Phase at gain crossover compared with 180. Therefore, 180 minus 161.56, you will be getting, if you calculate 180 minus 161.56, you will be getting 18.44 degrees. The phase margin is 18.44 degrees, 18 degrees 44 minutes. Right. In the similar way, if you calculate gain margin, if you calculate gain at phase crossover frequency, gain at phase crossover frequency, for this I am going to erase this part. Gain at phase crossover frequency, or else you can directly calculate gain margin as 20 log magnitude of inverse of the open loop gain. Inverse of the open loop gain means that is 10, and at omega is equal to omega PC, phase crossover. Omega is equal to omega PC means omega PC. What is omega PC? Omega PC is, we already got it, 10 root 2. 10 root 2 means 14.14. Therefore, if you put omega is equal to 14.14 or else 10 root 2, you will simply get the magnitude as 10 root 2 multiplied by under root 2 square, that is 2 plus 1, multiplied by under root 1 by root 2 square, that is 1 by 2 plus 1. Therefore, this will be is equal to how much? 20 log modulus of 3. So 20 log modulus of 3, this value you are going to get 9.542 decibels. Therefore, gain margin is 9.542 decibels and phase margin is 18.44 degrees. This is all about the first question. For the second question, let us just erase the other side also. So, second question is asked, like, if the gain margin is 20 decibels, then the value of K for this. If the gain margin is 20 decibels, gain margin is equal to 20 log modulus of 1 by gain of G of j omega at omega is equal to omega PC is equal to how much? This is 20 decibels. This implies, if this is equal to 20 decibels, then 1 by modulus of G of j omega at omega PC, that is phase crossover frequency, is equal to 1. So, modulus of G of j omega, we have already calculated that as 1 by modulus of g of j omega, you can calculate this to be k by 3. 1 by k by 3 is equal to 1. That implies you'll get k is equal to 3. For the gain margin to be 20 decibels, the value of gain, open loop gain, k must be is equal to how much? 3. This k by 3 we have already got from this part. And let us proceed to the next question now. So the question number 7, as you can see here, is something like this. For the system shown in the figure below, draw the Nyquist diagram and determine the closed loop stability if the plot for positive frequencies intersects the real axis at the first sub question, that is minus 0.81 plus J0, and the second sub question is minus 1.57 plus J0. Therefore, the open loop transfer function for the given question, given closed loop system is like this. G of s is equal to 10 times of k divided by s into 1 plus 0.1 s multiplied by 1 plus 0.01 s. The intention of giving k here is to indicate that upon varying the value of k, the plot for positive frequencies or else the negative frequencies is going to intersect the real axis at different locations, but it is not going to affect the nature of the plot. The nature of the plot is affected only by type and order of the system. Therefore, type of the system is 1 and order of the system, it is clearly evident, that is equal to 3. Type is 1 and order is 3. Therefore, the plot for this kind of system is going to be something like this. I am going to show it here. Type 1 means the starting phase is minus 90 degrees and magnitude is infinite. Starting phase is minus 90 and magnitude is infinite. And order 3, which means the ending phase is 270 degrees, minus 270 degrees. Therefore, the plot is going to be somewhat like this. Ending phase is minus 270 degrees and starting phase is minus 90 degrees. That is, at omega is equal to 0 plus, it starts at minus 90 degrees and infinite magnitude, and as omega approaches infinity, this approaches 0. And the Nyquist plot for negative frequencies is going to be exact mirror image of that of the positive frequencies. Therefore, this is the plot. This is the plot for negative frequencies, which means as omega is varied from negative infinite to 0 minus. Right? As the given system is an all-pole proper transfer function, the plot, Nyquist plot, is going to encircle the entire right half of S plane in clockwise sense, like this. So it is going to encircle the entire right half of S plane in this manner, like this. Therefore, we are asked to find out the closed loop stability under two conditions. The first condition is the point of intersection is at minus 0.81 plus J0. That is, the first point of intersection is this, minus 0.81, which means the critical point minus 1 is going to fall outside this plot. Therefore, this minus 1 plus J0 is not at all enclosing this minus 1 plus J0 point. The plot is not at all enclosing this minus 1 plus J0 point. So, from the Nyquist criteria, that is number of encirclements is equal to P minus Z, you need to understand this formula thoroughly, that see, the n is the number of encirclements in anti-clockwise sense. If the number of encirclements, if the encirclements are in opposite direction, that is in clockwise sense, then the number of encirclements should be counted negative. Therefore, n is number of encirclements of -1 plus j0 point in anti-clockwise sense. If the encirclements are clockwise, then they have to be counted negative, right? P is the number of open loop poles lying in right half of S plane, and Z is the number of closed loop poles lying in right half of S plane. Don't confuse Z with zeros. Z is the number of zeros of closed loop characteristic equation lying in the right half of S plane. Zeros of characteristic equation means poles of closed loop system. Zeros of closed loop characteristic equation means nothing but poles of closed loop system. Therefore, Z is the number of closed loop poles of the number of poles of closed loop system lying in the right half of S plane. Therefore, from this you can see it is not at all enclosing this -1 plus j0 point, which means the number of encirclements is 0. Therefore, n in this case is equal to 0. Therefore, 0 is equal to P, the number of poles lying in the right half of S plane. This was already given. The system is having all the poles in the left half of S plane only. Therefore, P is also 0. Number of poles lying in the right half of S plane is also 0. And P minus Z. Therefore, Z is equal to how much? 0. Z is 0 means the number of closed loop poles lying in the right half of S plane is equal to 0. Therefore, you can say the system is stable. And for the condition given in problem 1, that is, if the point of intersection is at minus 0.81 plus j0, the closed loop system is going to be stable. This conclusion we have drawn from the open loop Nyquist plot, the plot of the system in open loop configuration. From that we can conclude about the closed loop stability. So let us look at the second case. If the plot is intersecting the real axis at minus 1.57 plus j0. The second case is the point of intersection is minus 1.57 plus j0. So we need to conclude about stability in this particular case. So if the plot is intersecting at minus 1 plus j0, which means this point of intersection is going to be minus 1.57 plus j0. Therefore, this point minus 1 plus j0 is more to the right as compared to this minus 1.57 plus j0, which means this point is in this region, that is minus 1 plus j0 falls to the right of minus 1.57 plus j0. Therefore, the plot now encircles this twice. In which direction? Anti-clockwise direction. Therefore, the number of encirclements for this time is going to be how much? Number of encirclements, n is going to be equal to minus 2. N is equal to minus 2. That is equal to how much? P minus Z. P is anyway 0. P is the number of open loop poles lying in the right half of S plane. No open loop pole is lying in the right half of S plane. Therefore, P minus Z. From this, you can conclude Z is equal to 2. Z means the number of closed loop poles lying in the right half of S plane. Closed loop poles lying in the right half of S plane are 2, which means the closed loop system is unstable. The closed loop system is unstable in this case. Which case? When the plot is intersecting at -1 plus 1.57 plus J0. Therefore, the closed loop system is unstable in this particular case. So let's proceed to the next question now. So the question number 8 is like this. A system is modeled by state space model as x is equal to -2, 1, 2, -3 times of x plus 1 and 2, the matrix vector of 1 and -2 multiplied by U matrix, y is equal to 1, 0, a row matrix multiplied by x. Evaluate the state transition matrix with initial condition x of 0 is equal to 1 and 2 transpose. Therefore, the question is like this. Matrix A is given to be matrix A is equal to -2, 1, 2, -3, and matrix B is equal to 1 and -2. Matrix C is 1 and 0, a row matrix, and matrix D is anyways 0. So in order to find out the state transition matrix, we need to find out Laplace inverse of Si minus A. Therefore, Si minus A, just first evaluate Si minus A. Si minus A is equal to, simply multiply S with identity matrix and deduct this particular matrix A from that S multiplied by identity matrix. Therefore, it will be S plus 2 minus 1 minus 2 S plus 3. In order to find out Si minus A whole inverse, Si minus A whole inverse, we need to find out adjoint A divided by det. Adjoint of Si minus A divided by determinant of Si minus A. Therefore, adjoint of Si minus A divided by determinant of Si minus A is equal to 1 by determinant of Si minus A, S plus 2 into S plus 3, that is S square plus 6S, S square plus 5S plus 6 minus 2, that is S square plus 5S plus 4 multiplied by adjoint of A. Calculate the adjoint of A, that is S plus 3, 1, 2, S plus 2. This is Si minus A whole inverse. Therefore, we need to find out Laplace inverse of Si minus A whole inverse. Laplace inverse of Si minus A whole inverse is equal to Laplace inverse of this matrix S plus 3 divided by S plus 1 into S plus 4. If we just factorize this equation, it is clear the factors are 1 as well as 4. 2 divided by S plus 1, S plus 4. Next is 1 divided by S plus 1, S plus 4. And the other is S plus 2 divided by S plus 1, S plus 4. So, Laplace inverse of this particular matrix we need to find out. So, in order to find out its Laplace inverse, we have to split this particular matrix into its partial fractions. Therefore, Laplace inverse of this Laplace inverse of Si minus A whole inverse is nothing but state transition matrix phi of t. State transition matrix phi of t. That is equal to Laplace inverse of some A by S plus 1 plus some B by S plus 4. So for this moment, I am not calculating these values A and B. I am just directly noting these values as I have already pre-calculated, and you can calculate just by comparison of coefficients, right? Therefore, the value of A, in fact, all the coefficients are going to have 1 by 3 in common, and the value of A is 2 by 3, B is plus 1 by 3, and let us look at C. It is 1 by 3, that is 3 we have already taken common, minus 1 by S plus 4. So the other factors are 1 by S plus 1 minus 1 by S plus 4 and 1 by S plus 1 plus 2 by S plus 4. Therefore, Laplace inverse of this you can easily calculate. That is equal to 1 by 3, 2 by S plus 1, 2 e power minus t plus 1 by S plus 4, e power minus 4t. The other is e power minus t minus e power minus 4t. The next 2, this is going to be 2 by 3, as well as this is also going to be 2 by 3, right? Therefore, this is 2 e power minus t minus 2 e power minus 4t, e power minus t plus 2 e power minus 4t. Therefore, this is the state transition matrix we are going to get. The state transition matrix, I am writing it in short. State transition matrix is 1 by 3, so and so. This is the entire matrix. Therefore, with this we have successfully completed all the power pack questions, and all the best for your GATE exam. Thank you.